So this is a sputter. There are two ways to coat a sample for electron microscopy. One is evaporation. That means you make a metal or a carbon into a vapor, basically, that sort of coats everything. Drawback with that is that it's not so easy to, not so well defined. You sort of get some kind of coating, but you cannot decide the thickness and so on. It also creates like poor quality of the coatings. So a more modern way is to use a sputter. So a sputter works like a more or less like a spray can. It creates a metallic spray coming down from above onto the sample, and that is a very controlled method. So what should I say? The spraying goes on continuously over time. So either you can just run it for a certain amount of time, but an even better way, if you come closer here, is to use a crystal, a tuning fork. And this is called the thin film measurement crystal. So with this, we can measure the thickness while it is progressing. So you can program the machine to do a coating of a certain thickness. That's the fancy word. Okay. And also, in a sputter like this, you can choose different kind of targets. And now to change the target, you see when I'm lifting here, everything comes up, and the target is underneath here. And I can also pull, if I press here, pull here, this whole thing can be pulled up.
Okay.
And then I can unscrew here, remove the connector, and this is just a bayonet. You just pull by holding all the way in here, not over here, you hold all the way in here. And then you just pull, like that. Lift out the whole target. And the machine knows what target is mounted because from this pin combination. So here we have mounted Iridium. If you want to, for example, coat gold, you see I have one with 2 pins here, and the machine is programmed because we have mounted gold here. Okay. So you can buy all kind of targets. So why should I use gold and why is Iridium and so on? So I will talk a little bit about that now. Why do we coat the samples? Well, all the samples in an electron microscope must be electrically conducting. So if they are not electrically conducting, then we need to add an electrically conducting layer on top. So that's why we coat them. So if you have a metallic sample, let's say you work in metallurgical field, then you don't need to do the coating at all. But why should I use different types of metallic metals for my coating? Why iridium? Why not gold? Or why not aluminum or something else? That is a very important question. And the thing is like this. There can be many reasons. In the old days, we always coated the samples with gold because gold has excellent electrical conductivity and so on. The drawback is if you're going to do high resolution work, like you do in modern electron microscopy, when gold is sputtered onto the surface, it forms small droplets. And then you will see these droplets. So if you want to make very thin coatings, which is needed in high resolution microscopy, you need to use a metal that doesn't form drops. And iridium is the best metal for that. Okay. So with iridium, you can make that the thinnest coatings for the best performance. So iridium is usually used for coatings between 1 and 10 nanometer. 10 nanometer is for those days you want a little bit thicker coating. Standard is like 5 nanometer. Okay. If you're studying like, let's say you have nanoparticles, and the nanoparticles are like 5 nanometer. If you coat with 5 nanometer, that means the coating is the same thickness as the particle itself. So that will make a very bad, what shall I say, microscopy work, because you have, the coating will sort of soak. It's like you have like a snowfall on the sample, and you're trying to find things beneath the snow, right? So in that case, you want to go down. So then you can perhaps do a 1 nanometer coating. Okay. But the coating, the thinner you make the coating, the less it also performs its duty of making the surface electrical conducting and lead off the electrons. It also has another purpose, and that is that leads off heat. I mean, if you're running a high current, electric current in your microscope, the sample will heat up. So if your sample is sensitive to heat, making a thick coating can protect it and make it more easy for you to study. Many people try to shortcut or cheat, or shall I say, in sample preparation. So, I mean, there are ways to run without coatings. You can do tricks and so on, and then more on the advanced side. And the problem is that if you avoid doing a good coating, your work time on the machine is like 10 times more. So better to spend a little bit extra time here making a proper good coating for your task, then it will be easy downstream. And I mean, many people make poor coatings and then they suffer from charging in the sample, the image quality become bad, they need to do a lot of tricks to improve the performance, and then they spend a full day instead of like a 2-hour session. So if you want to make a thick coating, as I said, 5 nanometers is like default, works for 95% of all the people. But if you have a very rough material, like for example a paper, I mean the fibers in the paper is like 10 micrometer in diameter, so there's a lot of, in the microscope world, that is like huge roughness. In that case, your resolution, demand for resolution is probably not so high. I mean, are you going to study details on a single fiber? Well, then that's another case, right? But if you just want to study the paper and the fibers are like 10, 20 micrometers in diameter, that means we're talking about like 1,000, perhaps up to 10,000 times in magnification. That is low resolution work in electron microscopy. I mean, 100,000 to 1 million, that is the upper end of the performance. So if you have that case, then it's better to provide a good thick coating, and that's why you use gold. That's why I had a gold target. So then we can add a thicker gold coating instead. There is some other things to mention also, that is okay if you don't, I mean, there can be different needs in your work. I mean, one special need is like EDS, when you do energy dispersed spectroscopy, right? Then if you put on something, that will come up as a signal in, I mean, if, for example, the worst case, let's say you're working with iridium particles and you want to detect if you have iridium particles, then it will be very stupid to put iridium coating on top, because then you will measure iridium everywhere. So in that case, it can be wise to choose some other metal. In the old days, one did carbon. But carbon is usually very messy and creates bad coating. So in that particular case, you usually switch to chromium. And the advantage of doing chromium is that for chromium, there is no characteristic energy peak in the energy diagram. So it will be invisible, so it will not interfere in EDS analysis. The drawback with chromium, on the other hand, is that it oxidizes. So as soon as you have made a coating, you need to go to the machine, run your SEM session, and then the next day it will be fully oxidized, and then the coating is not conducting anymore. So then your sample is basically destroyed. So that is the drawback of using chromium. But so if you don't sort of work with iridium, then you can still, in EDS, you still coat with iridium, because you know that you don't have any iridium in your sample. There's no problem if you see an iridium peak. That is not an issue. But I mean, the main point I'm saying here, that there was an old tradition where you coated with carbon or you coated chromium in modern days. But 95% of EDS usage, you don't need to do anything on that. You can still do iridium. It's only when you have iridium actually that you want to study, then you choose chromium. Otherwise, you can still stick to iridium. So the machine has, you see, it's 2 cylinders. This one says carbon evaporation and dirty sputtering. So if we don't use iridium, then we use this cylinder. If we use iridium, then we use this cylinder. Okay. So here it says only for iridium and chrome. So we try to keep this a little bit more clean. So step 1 is to mount the samples, right? We have nice samples here prepared. Put them up here into the carousel. And since this one rotates, if your samples looks very same, then it is good to mark them underneath, so you don't get confused when they come out in a different position. Check also that the lid here is not closed. It should be open. Otherwise we cannot measure the thickness, right? And if I show you here in the drawer, here is the planetary gear system. So if we had that very poor sample of big particles and so on, mounting this carousel inside there, you see when this one rotates around, you get that kind of three-dimensional rotation that makes the spraying that comes from above coming in beneath in all the pores. Powder particles, we're talking about 100 micrometer or bigger particles, or very porous materials like a wood piece, a ship or something like that, and so on. Alright, and then we put on this. Make sure that the flange, the rubber fits. There's a button here on the back side. Turn that one on. This is a touch interface, but it's not super fast, so it's nice to use the pen actually. You can choose edit profile. So then we can create a profile here. I click new. Here we can choose different programs, but we want to do FM. That stands for Film Thickness Measured Terminated Sputtering. That means we use the crystal. And then we can choose a name here. And shall I write your name? What was it? And then we can also add that we're going to do a standard nanometer of Iridium.
Perfect.
So then you see here is your recipe, you can say. We can choose edit, and then we need to say, okay, the material should be Iridium, right? Iridium. Do you want to use the default? We always recommend that. So this is the default parameters, but here you see it says terminated thickness. It's already selected 5 because this is the normal. So if you want a different thickness, you can change this value, right? But for today, 5 is nice. Click OK, OK, and then we find your program here. First time it comes in the bottom of the list, but next time we start the machine, it will be in alphabetic order. You just click run, and the machine starts. This will take about 4 or 5 minutes or so. So first it's the, what shall I say, it just evacuates the pumping line. Then it starts to pump here, the chamber. And if this says 0, 0, 0, 0, 0, 0, that means we have a leakage here in the gasket. Okay. So then it's good to sort of hold here, so you see the percentage start to go up. But now it just started immediately. So now it's doing the pumping cycle. You see the pressure here starts to drop. The turbo speed's going up. It should go to 100%. And you see this note there. It says 4 to the power of -4. That is the pressure we want to reach. We are at like -2 now. So this will take 2-3 minutes. And after that, we will see that it says bleeding gas insertion or something like that. That means it puts back argon inside here. So the sputtering technique is it creates a plasma, an argon plasma, and then there is a magnet. Same way as we talked about the immersion lens system. That magnet will focus that plasma. Plasma is a gas of charged particles, right? And that will inject the plasma into the target, and that makes the target melt and form this spray of metal droplets that will come down onto the surface, and that's basically how it works. And meanwhile that spraying is ongoing, we can measure the thickness live here on screen. Now it just says 0 because it hasn't started yet. And when that one reaches 5 nanometer, it will shut off the machine, the vacuum will be released, and then you just open the lid, take out your sample, and turn off the machine, and you're done. So it's fully automated. It's like a dishwasher. Yeah, you can start back in there.